Good day, I'm Norman Wildberger. Today we're going to have a little introduction to something called the tropical calculus, which is an alternative way of thinking about the algebra of sets or multisets. It's a rather interesting, relatively recent innovation which goes under several different names. Tropical calculus, sometimes called the max plus algebra, sometimes minimax algebra. And it has its origins in control theory, and the tropical refers to the fact that there's some connection with Brazil. Now, I'm not actually that confident about the history. I think probably a number of different people have discovered some of these ideas sort of independently, but maybe some of you can inform us as to more details of what actually happened in terms of the development of this subject. So the framework is we're thinking about a number system, which for us might be the natural numbers, or the integers, or the rational numbers. And we're looking at this number system from the point of view of sort of the set theoretic or data theoretic point of view, where union, or max, and addition are the two main concepts we're going to be focusing on. So we have two numbers, x and y. We can talk about their union, which is just the maximum of those two numbers, and we can talk about their sum in the usual fashion. Now these two operations, so if we ignore the multiplication and the other operations for a second, these two operations together generate some interesting kind of algebra. And associated to them, there's sort of some secondary operations. So if we have union, we could also think perhaps in terms of the intersection or the minimum of two numbers. And the sort of inverse operation to addition, subtraction. And we've talked about how we can sort of think about various properties of these operations, forming something which we rather informally called a realm. And we could have a realm in the context of natural numbers, or also of integers, or also of rational numbers. Now, what motivates the tropical calculus is one particular law that holds in this system, which is this particular distributive law, that m plus n union p equals m plus n union m plus p. And I remind you that that means that if you take m and you add the maximum of n and p, that's the same as the maximum of m plus n or m plus p. It's kind of obvious, right? That you take m and you take the bigger of these two and add it to m. That's the same thing as looking at m plus n and m plus p, those two sums individually, and taking the maximum of those. Now this distributive law looks very much like the much more familiar distributive law, m times n plus p equals m times n plus m times p, that primary school students learn when they're learning about basic arithmetic. So the parallel here is that the addition here is sort of playing the role of the multiplication in the usual setting. And this union operation is sort of playing the role of the addition in the usual setting. And it's the parallel between these two types of distributive laws that really motivates the idea of the tropical calculus. So we might say that the basic idea of the tropical calculus is that we're going to replace these operations of union and addition with addition and multiplication respectively, and then exploit our familiarity with the usual algebra involving these two operations. So we're very familiar with algebra involving addition and multiplication, and we've just seen that these two operations behave a lot like these two, at least with respect to the distributive law. So the idea is, when we're working with these two operations in the realm context, what we do is we just replace these two operations with these ones and sort of pretend that we're doing ordinary algebra. Or more precisely, our familiarity with ordinary algebra allows us to relatively easily manipulate things here, which then have also some meaning in this context. So to set this up, I'm going to introduce my own particular way of doing this, which is a sort of an attempt to try to introduce this tropical calculus with a minimal amount of new notation. So I'm going to use just ordinary addition and multiplication, but to distinguish one of these new interpretations from the traditional one, I'm going to put a capital T in brackets to denote that this is a tropical equation here. So whenever we have an equation with a T, either before or after it, then we're going to interpret that equation in a tropical sense. And that means that we have to define very precisely what the meaning of all the various tropical equations are. So an equation with a T behind it has a new meaning that we are now going to establish step by step for a number of different kinds of different cases. So our basic setup is we're going to start with rational numbers. We could also, in fact, do this over the natural numbers or the integers, but the rational numbers is probably the biggest domain. That way we sort of include the other ones all at the same time. So x, y, and z are rational numbers. So let us define x plus y equals z tropical. Okay? That means that x union y equals z. So here's an ordinary equation with an ordinary meaning. This is the usual union that we already are familiar with. So this is saying that the union of x and y is z, or in other words, that the maximum of x and y is z. Okay? So when we have that connection between the three rational numbers x, y, and z, we're going to rewrite that this way using the symbol plus. X plus y equals z with a t. All right, so this plus sign in the context of a t really means union. Similarly, x, y equals z in the tropical context means that x plus y equals z. All right, so we're adopting the usual convention that xy means the same as x times y. So here's the operation of multiplication, but it's now a novel kind of multiplication. It means that x plus y equals z in the usual sense. So as a kind of a consequence of that, well, if x times y equals z means x plus y equals z, then y equals x to the n, tropically, is going to mean that y actually equals x plus x plus x plus x and so on n times. It's just multiplication n-fold. And since multiplication is addition, the meaning of this is that y equals n times x in the usual sense. Or that's ordinary multiplication. It's ordinary multiplication because there's no t there. This is a t. That means this has to be interpreted in this tropical sense. So, for example, 5 plus 7 equals 7 as a tropical equation. And that's because the union of 5 and 7 is 7. Union, of course, is the same as max. The max of 5 and 7 is 7. So this is the way we write that in the tropical sense. 5 times 7 equals 12 in the tropical sense. Because in the tropical sense, this multiplication really means ordinary addition. Ordinary addition of 5 and 7 is 12. So 5 times 7 equals 12 tropically. And tropically, 3 to the 4 equals 12 because in the tropical sense, multiplication is addition. And so this 3 to the 4 means really 3 plus 3 plus 3 plus 3, or in other words, the usual 3 times 4, which is 12. So these are certainly strange, new kinds of expressions, new usages of the operations addition and multiplication. Tropical kind of arithmetic. All right, so now we have some properties of these operations in this tropical context. We have, for example, associative laws, both for tropical addition and for tropical multiplication. And they're just the usual associative laws. And of course, they really reflect the associative laws of union and addition in the ordinary sense. Similarly, we have commutative laws for this tropical addition and tropical multiplication, which are just reflections of the commutative laws for ordinary union and ordinary addition. Then we have these distributive laws, which are sort of the motivating, laws that started this whole story, that x times y plus z equals x times y plus x times z, and the corresponding other one that's symmetrically arranged. X plus y times z equals x times z plus y times z. And this kind of law, this tropical kind of distributive law, is just a way of writing the law that we had before, that we wrote in ordinary terms as x plus y union z equals x plus y union x plus z. We're just rewriting that law using these new forms or interpretations of addition and multiplication. And now here are some laws that are not familiar in the usual story. So in ordinary addition, it's not true that x plus x equals x. But tropically, this is a very valid law. So x plus x equals x. It's just a reflection of the fact that x union x is always x. And this one, that 0 times y is the same as y times 0 is y, tropically. So that's a reflection of the ordinary fact that 0 plus y is the same as y plus 0 is y. So 0 is usually the additive identity. Here it's sort of the multiplicative identity. This idempotent kind of law is very important in applications because, first of all, we have to remember that it's valid. So it's a difference between the algebra here and the usual algebra that we're used to. And it's also important because it simplifies a lot of things. So if we have an expression that has, an xy term plus another xy term, well, that xy plus xy is the same as xy. That's what this law is telling us. So whenever we have copies or duplicates of something added together, we can just basically collapse those things. So things simplify quite often dramatically because of this idempotent law. Then we have some other observations that x plus 0 equals x tropically. That happens precisely when x is bigger than or equal to 0 in the usual sense. Right? This is saying that the maximum of x and 0 is x. X is a number, the maximum of x and 0 is x. It means that x is positive, greater than or equal to 0. And similarly, if x plus 0 happens to be 0 tropically, that's telling us that the max of x and 0 is 0. That means that x is less than or equal to 0. So the order properties of a number are reflected in this tropical setting by these purely algebraic relations. You can check that x to the n to the m is the same as x to the nm, because after all, x to the n really just means n times x. And if we replace that with n times x into the m, we're just again multiplying by m. So it's the same as just taking n times m copies of x. But now here this exponent nm is to be interpreted in the usual sense. So maybe that's a little bit possibly confusing, that the tropical multiplication does not apply to exponents. Okay, it applies to the variables themselves, but not exponents. Okay, so now we have the idea of inverses. So multiplication in this tropical setting is really ordinary addition. And ordinary addition has a nice kind of inverse. And so the inverse of ordinary addition is the negation. And so that negation then ends up playing the role of the multiplicative inverse in the tropical setting. So we can write that y equals x minus 1 tropical. That means that y times x should be 0, which is the multiplicative identity. It's like the thing that plays the role of 1 in the tropical world. And this is telling us that y plus x ordinarily is 0, or that y equals minus x. So the relation y equals x to the minus 1, or y equals x inverse, or y equals 1 over x, tropically is the same as saying that y is just the negative x in the ordinary sense. And that allows us then to make sense of quotients. So x over y equals z, well, that's the same as saying that x times y inverse equals z. And so tropically, that has the interpretation that x minus y equals z. So x over y equals z is the same as x minus y equals z. This is the tropical statement. This is the ordinary statement. It's a little bit fun, I think, playing around with these things. So it's good to have some exercises for you to practice getting yourself in this mindset of thinking differently about these fundamental, very familiar operations. So I'm going to give you some exercises for you to check and to just practice. So the first one is that show that x times z over y times z is equal to xy in a tropical setting. So in other words, that we are allowed to cancel common factors from the numerator and the denominator of a tropical expression, just as we ordinarily do in ordinary algebra. So corresponding to that, show that the same kind of thing does not happen or does not apply when we have an additive expression. So if we have the expression x plus z equals y plus z tropically, that from that we are not able to deduce that x equals y tropically. In ordinary algebra, you would just subtract a z and get that x equals y. But here you're not allowed to do that. Okay. You are allowed to cancel the multiplicative factors, but not the additive ones. So please convince yourself of that. Another important thing that we want to get our heads around is the role of the intersection, the other operation. So I remind you that the intersection of two numbers, x and y, can be expressed in terms of the addition and the union, in terms of this fundamental relation here, that x intersect y equals x plus y minus x union y. And from that we can deduce that this is the right way of thinking about how to interpret intersection in the tropical setting. So if z equals x intersect y, that's the same as z equals x times y over x plus y in a tropical setting. So why is that? Well, because over here, if we look at this equation here, we want to interpret this tropically. Okay, so if z equals x intersect y, that means that this is going to be z. So what is this thing if we want to interpret this or rewrite this equation in a tropical setting? Well, the x plus y is replaced with the x times y. And the x union y is replaced with the x plus y. And this thing minus this thing here is interpreted as a quotient. So it's this thing tropically divided by this thing tropically. So the tropical formulation of this ordinary equation is that z equals xy over x plus y tropically. So as another exercise to show that this is equivalent to the sort of harmonic mean condition, you can just sort of rewrite this as 1 over z equals 1 over x plus 1 over y. And you might like to sort of convince yourself that if you look at it in the right way, this is obvious or should be obvious. So here are some more exercises that show you that you can do algebra in this tropical setting. So show that x over y equals z over w tropically is equivalent to x times w equals y times z. So you can cross multiply to clear fractions just as you do in ordinary algebra. Similarly, that you can add fractions just as you do ordinary algebra. X over y plus z over w equals x times w plus y times z over y times w, tropically. Here, verify the identity that a plus bc over b plus c equals a plus b times a plus c over a plus b plus a plus c, tropically. And then here, use this identity to prove this other kind of distributive law between the unions and intersections, that A union B intersect C equals A union B intersect A union C. And I hope you can see that they kind of correspond. This B intersects C, that corresponds to BC over B plus C. We've seen that. And here's a union, so that corresponds to a plus. Here's an intersection between this and this, so A union B corresponds to A plus B, A union C corresponds to A plus C, and well, that intersection sort of corresponds to that. So hopefully it kind of makes sense. So this is a purely algebraic way of proving this distributive law. That's kind of interesting, I think. So a computer could sort of just algebraically prove this in this tropical setting. Proving this sort of algebraically in the ordinary setting is not so easy because our algebra is not really set up to easily work with these things. All right, so now as a sort of more weighty application, let's consider this following proposition. This is actually an example, sort of an arithmetical aspect of a very fundamental and important formula in set theory, or in sort of data structure theory more generally, called inclusion-exclusion. And we'll talk a little bit more about that in our next video. So here what we're saying is that for any rational numbers x, y, and z, we have the following relation that connects this union with sums and differences involving intersections. So it's saying that x union y union z, and this means the maximum of x, y, and z, is x plus y plus z minus x intersect y minus x intersect z minus y intersect z plus x intersect y intersect z. So for example, if x happens to be 2 and y is 5 and z equals 3, then the left-hand side here is 2 union 5 union 3. That's the maximum of those three, which is obviously 5. The right-hand side would be 2 plus 5 plus 3 minus, okay, the meat of 2 and 5, the meat of 2 and 3, the meat of 5 and 3, or the intersection, and then the addition of the intersection 2, intersect 5, intersect 3. So 2 plus 5 plus 3 is 10. The intersection of these two is the minimum, that's minus 2. Here there's another minus 2. Here there's a minus 3. And then we have to add the minimum of these three, which is 2. So altogether we get 10 minus 5, which is 5. Does in fact equal the left-hand side. All right, so if we wanted to prove this sort of using our framework of the tropical calculus, sort of a fun thing to try to do, one thing that we might first do is to bring the negatives here to the other side so that we just have additions involved. So we're going to rewrite this equation star as star star, where we have the union of all three here, and then plus x intersect y, plus x intersect z, plus y intersect z, so we brought those three to that side, equals x plus y plus z plus the intersection x intersect y intersect z. So let's see if we can prove this tropically. So we want to just prove that this is an identity, like a plus b squared equals a squared plus 2ab plus b squared, the same kind of identity. But we're going to do it tropically. As a preliminary to that, let's just get under control how to represent this intersection of three things effectively tropically. So I remind you that x intersect y equals w. That means, or can be interpreted in a tropical setting as saying that w equals x times y over x plus y. That's sort of the way intersection looks like in this tropical framework. Okay, so if we have three things that we're intersecting, we can think about that as the intersection of x with the intersection y intersect z. So it's going to be x times, and here is the y intersect z expression tropically, yz over y plus z. So x times that divided by x plus that same quantity. So this thing equals w is the same as the tropical equation that this thing equals w. Now, one of the things we're allowed to do with this kind of expression is multiply top and bottom by the same quantity. So we could multiply top and bottom by y plus z, sort of to clear the denominators that are naturally there. Then we'll get x, y, z in the numerator. And after we've multiplied by y plus z, then we'll have here in the denominator x, y plus x, z plus y, z. So we get this sort of nice symmetrical expression that this intersection equals w. On the tropical side, it means that w equals xyz over xy plus xz plus yz. It's not hard to see that this is equivalent to 1 over w equals 1 over x plus 1 over y plus 1 over z. You just sort of take the inverses of both sides there. So now we have control over the intersection of three things. So let's have a look if we can prove that relation tropically. All right, so here's the equation that we wanted to establish. We want to establish this identity. X union y union z plus x intersect y plus x intersect z plus y intersect z equals x plus y plus z plus x intersect y intersect z. All right, so we're going to take that equation and rewrite it tropically. So we're going to replace the unions with additions, and we're going to replace the additions with multiplications. And we're going to replace these intersections with these more complicated expressions. So x intersect y gets replaced with xy over x plus y. Similarly, this gets replaced with that gets replaced with that. The x plus y plus z gets replaced with x, y, z. And this term here is that thing that we just had a look at in the previous slide. That's xyz over xy plus xz plus yz. And that has to multiply this because there's an addition sign there. Right? So we're going to get this original thing here is x plus y plus z, and then we're going to multiply that by this expression, multiply by this, multiply by this. That's equal to xyz times this product here. So we have to establish this as an identity in the tropical setting. Right, so we look at it, and we see that there's a common factor of x, y, z squared on both sides. There's an x, y, z squared there. And these terms here gives us another x, y, z squared. And we can cancel them, because we can multiply both sides by the inverse of x, y, z, which always exists. In fact, it's even nicer than the usual inverse. Usually you have to worry about something being 0 because you're not allowed to divide by 0. Here, there's no problem. There's no possibility of dividing by something not allowed, because even 0 is allowed to. 0 is sort of playing the role of 1 here. Okay, so after we cancel those x, y, z squareds, which are common, then we can clear denominators. Okay, so we're going to sort of just, it's something a over b equals c over d, so we'll just rewrite that as a times d equals b times c. So we're going to get this expression times the denominator here. We want to show that that's equal to the denominator here times the numerator here. So this comes up there. So this is the identity that we need to realize. And then we just do that by expanding both sides. So when you expand, say, this left-hand side, you're going to get x times xy, so that's going to be an x squared y. And then there's going to be an x squared z. And then there's an xyz. There it is there. And then there's a yxy squared. And then an yxz. Well, that's the same as the xyz that we've already got. So now we have two of them. But two of them is the same as one of them, because of the idempotent identity. X plus x is the same as x. So x times y times z plus x times y times z is still just x times y times z. You never get more than one of anything. So after we expand these terms, then we see that we get sort of these 6 symmetrical terms plus x, y, z. And then if you look on the right-hand side, what you get when you expand that, you see that you get exactly the same terms. So this equals this is an identity in the tropical world, where we've crucially used the idempotent law. And so the original thing is a true identity. And we've proven this law of inclusion-exclusion, at least in the context of rational numbers. Still not sort of at the level of sets, but in the context of rational numbers, we've proven this inclusion-exclusion sort of identity. This is a very sort of lighthearted, I guess, introduction to the tropical calculus. It's very much sort of geared towards the applications that I'm kind of interested in here, which are to data structures and in particular the role of multisets. So you know, if you look up max plus algebra, minimax algebra, you will find many other directions that people go in. This is not sort of the primary direction, but I think it's a nice kind of amusing, and more than amusing, it's sort of instructive to think differently about such very fundamental things as the basic operations of arithmetic, different ways of realizing and thinking about them. So in our next video, we're going to look more carefully at this principle of inclusion-exclusion, which is actually a very fundamental law in set theory. In fact, it's one of the pillars of set theory, a law with wide application. And we're going to prove it, but we're also going to formulate it in a more general fashion than usual. So one of the themes that I'm pushing here a little bit is that we don't just have set theory, we actually have LOMs, lists, ordered sets, multisets, and sets. And for many purposes, multisets have really been not given their proper due. So we're going to see that thinking about things in terms of multisets, rather more generally than just sets, allows us to understand the principle of inclusion-exclusion, I think, in a deeper and a more fundamental way than the usual way. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.